We have been discussing about compressible flows, and we will continue with a very interesting concept in compressible flows known as shock. So, first of all, I intend to give you a physical perspective. For that, let us say that there is a supersonic flow, that is flow with a Mach number greater than 1, with that means the disturbance velocity divided by the sound velocity is greater than 1, rather disturbance speed by sound speed is greater than 1. So, what it means is that the disturbance source, so u is the speed of the source of the disturbance, not the speed of the disturbance. So, and c is the speed of the disturbance, which is the sonic speed. So, what it essentially means is that the disturbance source moves at a speed which is greater than the local sonic speed. So, when that happens, this kind of Mach cone is formed, which we discussed earlier in the context of understanding the significance of Mach number. So, there is a region which is the zone of influence, which is this one, and this is like the zone of silence. Now, let us imagine that this Mach cone is generated because of a aircraft moving in this direction. So, if the aircraft is stationary, the air is moving in this direction to interface with it. So, when it does so, suddenly when it crosses this borderline of the zone of silence and the zone of influence, this is the zone of influence, there will be a sudden discontinuity in what you see, and this discontinuity can be manifested in the form of a discontinuity in various properties like pressure, density, temperature and so on. So, if you have a supersonic flow, the physical origin of this discontinuity is that the source of disturbance propagates at a speed which is faster than the disturbance speed itself, and therefore, the disturbance accumulates, tends on accumulating at certain locations where this sort of large accumulation may be released in the form of propagation of a wave called as shock wave. So, the shock wave can form in various ways. For example, you can have a shock wave where the direction of flow is such that the front of the wave across which you have a discontinuity is perpendicular. So, this is called as normal shock. On the other hand, if the angle is different from 90 degree, it is called as oblique shock. So, so far as the purview of this course is concerned, we will primarily discuss on normal shock. So, theory of normal shock. So, let us say that this is the shock front. On the upstream of the shock, the pressure is P1, the density is rho 1, velocity is u1, temperature is T1. Okay. And at the downstream of the shock, pressure is P2, density is rho 2, velocity is u2, temperature is T2. There is an abrupt discontinuity across this. Our objective is to relate these downstream properties with the upstream properties and figure out that under what circumstances characterized by the Mach number the shock will occur. Physically we have discussed already that the Mach number occurs, the shock occurs only for, or the possibility of the shock to occur appears only when the flow is supersonic, that is the Mach number greater than 1. Why the opposite does not occur? We will come to that subsequently as we go ahead with the theory of normal shock. So, what we do is we imagine a control volume built around the shock front. Okay. So, once we do that, let us say this is a very thin control volume because it is, the shock is an abrupt discontinuity, but it will still have a area of cross section, say A. So, we will apply the mass balance, momentum balance and energy balance for this. So, let us start with mass balance. Or continuity. Now, can you tell, first of all, before doing the things mathematically we have to understand it physically. So, while considering the usual sound wave, we also consider a front across which say P changes to P plus dP, U changes to U plus du and all those things. So, what is the difference between that kind of a wave and this kind of a wave? That kind of a wave is called as a weak wave because there is no abrupt discontinuity of properties across the wave front. Now, this is like a, this is a strong wave because there is abrupt discontinuity of properties across the front. So, if this is P, you cannot consider this as P plus dP, this is different from this P which is finitely different, not infinitesimally different. That is the difference between the previous analysis that we did and the shock wave analysis that we are doing at this moment. So, continuity you can write rho 1 u1 a is same, for all these substances we are assuming ideal gas model. So, we can write rho as P by RT now U by C is equal to the Mach number and we can write U is equal to root over gamma RT, sorry C is equal to root over gamma RT, not. So, C is equal to root over gamma RT, therefore, U is equal to m root over gamma RT. I want to tell you something which is fundamentally very interesting here. How did we derive this root over gamma RT? We derived this on the basis of a consideration that the process is isentropic. So, recall that it is the partial derivative of pressure with respect to density that was going to give us the square of the sonic speed. So, then what we did is we calculated the partial change of pressure with respect to density by considering an isentropic process, and that is how for an ideal gas we have come up to this relationship. The process by virtue of which the shock takes place is by no means isentropic, but still we can use this. The reason is that this we are using as a property. So, this a property, once it is used, it is not a function of the process by which the property is arrived at. So, the property may be derived considering certain processes, but once it is derived and it is used, it can be used for any process. So, you so next is you write P1 by RT1, U1 is M1 root over gamma RT1 is equal to P2 by RT2 into M2 root over gamma RT2. So, from this I am trying to write in one corner of the board what is the gist of this, that is P1 M1 by square root of T1 is equal to P2 M2 by square root of T2, right. This let us say is equation number 1 what we have got from continuity. Then we have momentum balance. So, after continuity we will have momentum balance and then we will consider energy balance. So, momentum balance. P2 minus P1 into A so it is rather let us write minus of P2 minus P1 into A, because P1 is in this direction and P2 is in this direction, right. So, along x the force is minus of P2 minus P1 into A. So, this is equal to m dot into U2 minus U1 by momentum theorem. M dot is rho A into U2, rho 2 into A2 into U2, but it is also same as rho 1 into A1 into U1. So, you can write it rho 2 A2 sorry A is common, rho 2 A U2 square minus rho 1 A U1 square. So, you can clean it up and write P1 plus rho 1 U1 square is equal to P2 plus rho 2 U2 square, right. Very interestingly, see one thing, had we been in a position to use the Bernoulli's equation, it would be P plus half rho U square. So, that half factor is gone because of the irreversibility in the system. So, now we can make certain simplifications. Rho 1 is P1 by RT1, rho 2 is P2 by RT2, U1 square is M1 square into C1 square, C1 square is gamma RT1. Similarly, sorry, I have written in place of P, I have this is P. This is the consequence of poor handwriting, you know, P is looking like rho and rho is looking like P. This is P2 plus, so this should be here. So, U2 square is this. So, P1 into, now RT1 and RT1 gets cancelled, 1 plus M1 square into gamma is equal to P2. Similarly, you will get 1 plus gamma M2 square. So, I will write equation number 2 here, P1 into 1 plus gamma M1 square is equal to P2 into 1 plus gamma M2 square. This is equation number 2. Third is energy equation. So, energy equation H plus H1 plus U1 square by 2 is equal to H2 plus U2 square by 2. This is essentially first law of thermodynamics applied between the two sections, assuming, you know, uniform property across the sections, neglecting changes in potential energy. So, you have enthalpy, which is internal energy plus flow energy. So, because this course does not consider thermodynamics as a prerequisite, I would like to give you a brief idea that why this, how this enthalpy comes in the energy equation. So, when a fluid is flowing with thermal effects, its energy, in addition to kinetic energy, potential energy and flow energy, these three forms of energy we have studied in the context of Bernoulli's equation, we have another form of energy which is internal energy. So, the internal energy is also the intrinsic thermal part of the energy that would have been the case when there would have been no flow. With flow, the total thermal energy is internal energy plus flow energy, and these two together, this is P by rho again, this is together known as enthalpy H. So, that is why you have this equation in this particular form. So, now for an ideal gas you can write dH equal to Cp dt, and we are assuming that it is a calorically perfect gas. So, you can integrate from 1 to 2, Cp is a constant for a calorically perfect gas. So, you can write in place of H2 minus H1, you can write Cp into T2 minus T1. So, on this side you write Cp T1, on this side you write Cp T2, that we will write separately. U1 square is what? U1 square is M1 square gamma R T1. So, the next job is to express Cp as a function of gamma. So, you can write gamma is equal to Cp by Cv and Cp minus Cv is equal to R. So, Cp minus Cp by gamma is equal to R. So, Cp into gamma minus 1 by gamma is equal to R, that means Cp is equal to gamma R by gamma minus 1. So, gamma R by gamma minus 1 T1 plus M1 square gamma R T1 by 2 is equal to gamma R by gamma minus 1 T2 plus M2 square gamma R T2 by 2. So, T1 into 1 plus you multiply both sides by gamma minus 1. Right. Just check it once, hopefully it is correct, right. So, you can write equation number 3 Now, before doing further manipulation, let us discuss a bit what we want to do actually. So, in these equations you can clearly figure out that if you know, you always know M1 before, that is the Mach number before shock. If you know M2, then from information of P1 you know P2, from T1 you know T2. Similarly, from P01 you can find out P02, from A1 star you can find out A2 star. So, all the properties which are reference properties for an isentropic flow, the jump in those properties you can calculate only with the key that you know what is M2. So, during isentropic flow, that is isentropic flow, we are assuming that it is taking place before shock and even after shock, only just during the shock the isentropic nature is disturbed. It is adiabatic because it is very rapid, but it is considered to be irreversible and adiabatic. Okay. So, what is missing as an information is the Mach number immediately after shock, because if you know what is the Mach number immediately after shock, then based on that Mach number you can calculate the new temperature, the new pressure, the stagnation pressure, the stagnation temperature, and also new A star. So, all these things you can calculate. So, the objective of our algebraic manipulation will be to relate M2 with M1. So, to do that, in equation 1 we have P1 by P2. So, in equation 1 this P1 by P2 we will write 1 plus gamma M2 square by 1 plus gamma M1 square is equal to M2 by M1 into square root of so P1 by P2 we have written, this we have taken care of, M2 by M1 we have written. So, then the remaining is square root of T1 by T2. Square root of T1 by T2 is 1 plus gamma minus 1 by 2 M2 square by 1 plus gamma minus 1 by 2 M1 square. In other words, we square both sides, and this is the relationship that we have. Only one issue is that conceptually this is okay, but algebraically this is not an explicit relationship between M1 and M2 or M1 square and M2 square. So, what we need to do is we need to derive an explicit relationship between M1 square and M2 square from here, that we will take up in the next lecture. Thank you very much.